Welcome to the first lecture of module 3. In this module, we are going to discuss interpretation or analysis of the batch reactor kinetic data. Before going to this lecture, let us have small recap of our earlier lectures which we had in module 2. In module 2, we have basically covered stoichiometry and introduction to the stoichiometry. Then we have considered the limiting reactants in case of stoichiometry. We have considered two reactors, one is batch reactor and another is flow reactor, and for both cases we have considered constant volume batch and flow reactor and how to obtain the stoichiometry in that system. And finally, we have considered stoichiometry in variable volume batch and flow systems. So, each systems we have completed with different examples. Now, in this lecture we will consider analysis of the batch reactor kinetic data, and the lecture outline would be introduction to the batch reactor kinetic data, then constant volume batch reactor, then we will consider integral method of analysis. So, we will consider integral method of analysis in this lecture, and to take the batch reactor data and then we will analyze for different kinetics. First, we need to know the what is rate equations, although we have introduced at the beginning. Rate equation means it is the dependency of the concentration with the rate of the reaction. The reactions which happens, if we represent them mathematically, then we call rate of reactions. So, how to characterize the rate of reactions? We can characterize rate of reaction by suggested which can be obtained or suggested from theoretical consideration. So, theoretically we can obtain the rate expression, or it can be obtained results of an empirical curve fitting. So, in either case the rate coefficient can only be found by experiments. So, whether it is empirical curve fitting or it is theoretical consideration, whatever may be the rate of the reactions or the rate equation suggests, the constant value or the rate coefficient values can be obtained only by experiment. So, we have to perform the experiment in different reactors and obtain the kinetic data. How to determine a rate equation? So, we need to obtain the rate equations, but how we can obtain the rate equation? To obtain the rate equations, we need to follow two different procedures. One of them is the concentration dependency is found first at fixed temperature and then the temperature dependency is found. So, concentration dependency, if we have to find out, we have to keep the condition isothermal. So, we need to keep the temperature constant and vary the concentration and obtain the kinetics. So, then dependency of concentration can be obtained at a fixed temperature. So, that is the first thing we can do. Now, we have to fix the concentration and then we obtain the temperature dependency, we vary the temperature. So, this combine these two things will give the overall rate equations which is a function of temperature and concentration. Now, experiment for determination of extent of reaction. So, how to obtain the extent of chemical reaction, how to determine experimentally. This can be obtained by two methods, one is using batch reactor or second is using flow reactor. So, in case of batch or flow reactor, the method we generally follow to obtain the extent of reactions, we need to follow certain procedures. We can do by following the concentration of a given components. So, we can see in a particular reactor, we can see the change of concentration for a given component, or we can follow the change of some physical properties of the fluid or of the reactants which we have given. Physical properties like electrical conductivity or refractive index. The change of these properties we can follow in a particular reactor. We can also follow the change in total pressure at a constant volume system. That means, if the reactions happen in gas phase, we can see the change of partial pressure of a particular component at constant volume systems. Or we can also see the change in volume in the system if we keep the pressure constant. So, this way these four methods we can follow for any type of reactors like batch reactors or flow reactors, whatever may be the reactors we choose, but we can see this property change with time. Now, between these two reactors, batch reactors and flow reactors, which one we should use for doing the kinetic analysis? If we consider batch reactor, it is usually operated at isothermal conditions at constant volume, and it is very simple device and it can be adaptable to any laboratory setup. It needs but little auxiliary equipments or instrumentation. So, very little auxiliary equipments we can perform the batch reactor kinetic experiments. Very simple operation, and it is helpful for homogeneous kinetic data. So, if our system is homogeneous, that means if we have more than one reactants, if they react together in a homogeneous solvent, then this batch reactor is helpful to obtain the kinetic data. So, generally in most of the homogeneous kinetic data experiments we perform using the batch reactor. For flow reactor, this is generally used to study the kinetics of the heterogeneous reactions. So, which we will discuss in the later part. So, or it may be covered in case of your chemical reaction engineering 2, where most of the catalytic and heterogeneous reactions are covered. So, for the time being we will consider batch reactor kinetic data analysis. To do the batch reactor kinetic data analysis, the two procedures we generally use, one is called integral method. In integral method, the other method is the differential method. So, these two procedures we generally use to obtain the batch reactor kinetic data. In integral method, what we do, we guess a particular form of rate equation. So, first we have to guess a particular form of rate equation, then we need to integrate the equation and manipulate mathematically. So, if we integrate the rate expression, we generally get the concentration profile, that means the concentration versus time, how the concentration in a reactor varying with time. So, we integrate the rate equations which we guess and then manipulate mathematically. Now, we plot the concentration change versus time. So, we plot concentration versus time. If this yields a straight line, then the rate equation is said to be satisfactorily fit the data. So, the rate equation should be straight line, fit all the kinetic data in a straight line. If that is obtained, then we can say that the assumed rate expression or guessed rate expression is the correct one. In case of the differential method, what we do, feed the rate expression to the data directly without any integration. So, we do not do any integration of the differential form of rate expression, because the rate expression is itself a differential form, and we take the data directly to feed the differential form of the equation, which we do not integrate. Now, between the integral and differential method, which one is beneficial and what are their advantage and disadvantages? In case of integral method, it is very easy to use, because we take a rate, we guess a rate equation and then we integrate it and then we feed the data which we obtained. So, it is very easy to use and recommended for testing specific mechanism. So, we can assume a specific mechanism and according to that we can obtain a general order rate equation and then we test and whether it is the mechanism is following as per the guessed kinetics. It is relatively simple rate expression. So, or when the data are so scattered that we cannot reliably find the derivatives needed in the differential form. So, if the kinetics data are scattered, it may so happen that generally for kinetic experiments there are large deviation from the getting the kinetic data, because it depends on the reactants and depend on the rate of the chemical reactions. If the reaction is very fast, its change within a period of time, change of the concentration which is happened within a stipulated period of time, we may not get the exact kinetics and the change we may not get properly. So, the data generally scattered. So, in that case the derivative method or the differential method we cannot use. In that case the integral method become more easy to apply. In case of differential method, it is more useful for complicated situations and require more accurate or larger amounts of data. So, if we have large amount of data and data are not scattered, the data are very accurate, in that case more complicated situation we can handle with differential method. It can be used to develop or build up a rate equation to fit the data. So, we can use the differential method to develop or build up a rate equation to fit the data. So, whereas in integral method we have to guess the rate equation, but in case of differential method we can develop the rate equation. So, the general practice among these two methods, in general it is suggested that the integral method of analysis be attempted first. If the integral method is not successful, then we will use the differential method. So, this is the general procedure to be followed to obtain any rate expression. Now, reaction rate for constant volume batch reactor. So, when we talk on constant volume batch reactor, it means that the volume of the reactant, not the volume of the reactor. So, the amount of volume, the amount of reactants and its volume represents the volume of the batch reactor, but it is not the volume of the reactor. So, this essentially refers to the constant density reaction system. Constant volume reactor means volume of the reaction mixture. And this is actually represents the constant density reaction system. Most of the liquid phase reaction or if the reaction of the gas phase is happening in a constant volume batch. So, gas phase reaction in constant volume batch, constant volume bomb. These are falls under the constant volume systems. Now, for a constant volume reactant I, which is happening in a constant volume reactor, we can write the rate of reaction or Ri is equal to 1 by V dNi dt, which is equal to d Ni by V dt, because since volume is constant. So, this we can represent dCi dt. Now, if the reactions is happening in the gas phase and the gas phase is ideal, we can write the concentration term C for ideal gas phase. C would be equal to P by RT, that means P is the partial pressure of that components. So, we can write this expression Ri would be equal to 1 by RT dPi dt. Now, let us introduce another term which is conversion. The conversion or the fractional conversion of any reactants, say A, can be represented with a symbol fractional conversion of component A is can be represented with XA, or we simply call the conversion of E. Now, suppose we had initially Na mole of component A. So, Na is the initial amount of reactant A at time t equal to 0. and Na is the amount present at any time t. So, we can write the conversion for a constant volume system, that is X A would be the initial amount minus the amount present after time t divided by the initial amount. So, this we can write 1 minus Na by Na naught. Now, if we just divide the numerator and denominator here by V for constant volume system, we can write 1 minus Na by V divided by Na naught by V. So, we can write 1 minus Ca by Ca naught. Now, if we differentiate these equations, we will have relation between x a dx a with dca. So, we can write dx a would be equal to minus dca by ca naught. So, this is the relations in terms of the differential form of fractional conversion with the change in concentration. Now, integral method of analysis, the general procedure as we have said for any integral method of analysis, what we need to do? First, we need to get the particular form of rate expression. So, we have to get particular rate equation which to be tested by integration. So, we assume a particular rate equation that will be integrated in a particular form, and then the second step is to plot concentration versus time. And that would be with the experimental data. So, if you do so, if the fit which we have done with this, if this is satisfactory, then we will get the appropriate rate equations, and if it is unsatisfactory, then guess another rate form. And then similar procedure would be followed. So, this is the general procedure. Next, we will consider the unimolecular first order reactions, irreversible first order reaction. Let us consider a general reactions which is A2 products. Now, if the, as we said, this is first order reaction, so the red equations we can write minus R A is equal to minus d C A d t would be equal to k into C A. If we separate the variables from here, we can write d C A by C A would be equal to k into d t. Now, if we put the integral for both the cases, it would be from C A naught, which was is the initial concentration, to C A at any time t. So, initially t equal to 0 to any time t. So, with this limit, if we integrate this expression, it will be ln C A from C A naught to C A would be equal to k into t. So, if we substitute this, this would be minus ln C A minus ln C A naught is equal to k t, and from here we can write minus ln C A by C A naught would be equal to k t. So, this is in terms of the concentration profile. We can also write C A by C A naught would be e to the power minus k t. We can write C A would be equal to C A naught e to the power minus k t. So, this is for concentration profile for first order reaction. Now, this expression we can write in terms of the conversion. So, in terms of conversion, we can write as we have seen earlier that dCA dXA is equal to minus dCA by CA naught. So, if we substitute in the red expression, that is minus dCA dt would be equal to kCA, we can write and CA is equal to CA naught into 1 minus XA. We can write this expression as dXA dt would be equal to k into 1 minus XA. Now, if we integrate this expression, we would obtain so we can get minus. So, by separation of the variables we can write dxa by 1 minus xa would be equal to k into dt. Now, if we integrate with a limit when t is equal to 0, the conversion is xa is 0, and when t is equal to t, the conversion is xa. So, if we integrate this, this would be minus ln 1 minus xa would be equal to kt. So, from here we can write xa is equal to 1 minus e to the power minus kt. So, this is in terms of the conversion. So, we can write both in terms of the concentration or in terms of the conversion. Now, if we plot say this y axis is time and x axis we can plot Ca ln Ca by Ca naught or ln 1 minus xa. So, we have two expression, one is this one, another one is minus ln Ca by Ca naught is equal to kt. So, if we plot ln Ca by Ca naught versus t in this expression, as you can see, it will lead to a straight line with a slope k. Similarly, from this expression, if we plot ln 1 minus xa versus t, we will get a straight line. So, if we have the rate data obtained from the batch reactor, we can feed the data and it will lead to a straight line passing through the origin with a slope is equal to k. So, if the data fits in a linear curve straight line, then the kinetics which we guessed as a first order kinetics will be obtained. But if we look into the rate expression, although it is first order, but in different forms. Suppose if the rate expression is like this, minus dca dt is equal to k into Ca to the power 0.6 and Cb to the power 0.4. So, as we can see, the overall order of the reaction is 1. So, this is also first order reaction. So, overall order for this rate expression is 0.6 plus 0.4. So, which is 1. So, although this rate expression is of the first order in nature, but it is not amicable for the solution using integral method, is not amenable to the integral method of analysis. So, the caution over here is that not all first order reaction can be treated as the integral method explained before. So, not all first order reaction can be treated as discussed. Now, let us consider the second order kinetics, irreversible second order reactions. So, if the reaction is second order, let us consider a general reactions which is A plus B forming products. If we write the rate expression for this second order reactions, we can write minus R A is equal to minus d C A dt is equal to minus d C B dt, which we can write k into C A into C B. Now, the conversion, if we consider x A for component A, the amount of A which will be reacted is x A C A naught x A. So, this is the amount reacted, and let the initial concentration of A and B A is C A naught and B is C B naught. So, we can write the concentration at any time t C A would be C A naught minus C A naught x A, and C B naught would be C B naught minus C A naught x A. Now, if we substitute in this rate expression, we can obtain minus R A would be equal to C A naught into d x A dt. How we obtain d x A dt? If we differentiate this expression, this one, it would be d C A would be equal to d C A dt would be equal to minus C A naught d x A dt. So, if we substitute here this minus d C A d x A minus C A naught d x A dt in this expression, it would be C A naught d x A dt into, which would be equal to k into C A. In this expression, C A would be C A naught minus C A naught x A into C B naught minus C A naught x A. So, then we will obtain k into C A naught square 1 minus x A into C B naught by Ca naught minus x A. Now, let m is equal to C B naught by C A naught. So, if we assume that m is equal to C B naught by C A naught, we can write this expression as C A naught dx A dt would be equal to k C A square 1 minus x A into m minus x A. So, from here C A naught will cancel out. So, you will have dx A dt would be equal to k C A naught 1 minus x A into m minus x A. Now, if we do the separation of the variables of this expression, so separation of the variables, we will obtain dx A by 1 minus x A into m minus x A would be equal to C A naught into k integral 0 to t dt. So, it would be 0 to x A. Now, we have to break down into partial fractions of the left hand side. So, break down partial fractions. So, to do that we can write this 1 by 1 minus x A m minus x A. This we can write 1 by m minus 1 into 1 by 1 minus x A minus 1 by m minus x A. Now, if we substitute this over here and then we do integration, we will obtain from here we can write 1 by m minus 1 integral 0 to x A into 1 by 1 minus x A minus 1 by m minus x A into dx A would be equal to C A naught k integral 0 to t dt. Now, if we integrate this expression, this would take the form ln 1 minus x b divided by 1 minus x A, which is equal to ln m minus x A divided by m into 1 minus x A would be equal to ln C B C A naught divided by C B naught C A equal to ln C B divided by m into C A, which is equal to C A naught m into k T, which is equal to C B naught minus C A naught into k T. So, that this equation, as you can see, this is only valid when m not equal to 1. So, when m is equal to 1, this is undefined. So, this equation cannot be valid. Now, if we plot the concentration versus time, so we will obtain this is ln Cb by Ca versus time. So, if we plot, then we will obtain, this is 0, we will obtain a curve like this, which is so the intercept here is ln Cb naught by Ca naught, that is ln m, and the slope of this curve would be equal to Cb naught minus Ca naught into k. Now, if we plot like this, similarly with 0 0, this is time and this is ln m minus x a divided by m into 1 minus x a, or we can plot ln Cb Ca naught by Cb naught Ca. So, if we plot, then we can obtain a curve which is passing through the origin, a straight line with a slope is equal to Cv naught minus Ca naught into k. So, this way we can interpret the second order rate expression by integral method, and if the concentration of component B is such that the change of concentration due to the reaction of A and B, the change of concentration of B is negligible, that means the component B is present in large excess. So, its concentration does not change much. So, in that case this equation will reduce to the pseudo first order reaction. Let us consider two different caution. One is if the reactants introduced in equivalent amounts. So, equimolar or stoichiometric amount. So, in that case Cv naught by Ca naught, that is m, is equal to Cv naught by Ca naught. If Ca naught is equal to Cv naught, that is stoichiometric amount, then m is equal to 1, and then the treatment which we have done before is not valid, or if the reactions in 2 moles of A reactants and producing some products will be treated in a different way. Like if we have twice A 2 products, in that case we will get the rate expression is minus R A would be equal to minus dCA dt, which is equal to k into Ca square, which is equal to k into Ca naught square into 1 minus Xa square. Now, if we integrate this expression, then we will obtain 1 by Ca minus 1 by Ca naught would be equal to 1 by Ca naught into Xa by 1 minus Xa, which is equal to Kt. Now, if we plot this expression, so we would obtain the curve like this. So, 1 by Ca versus time. If we plot for the equation 1 by Ca minus 1 by Ca naught is equal to Kt. So, in that case we will obtain a straight line passing through some point on the y axis. So, this means this is your intercept, which is 1 by Ca naught, and the slope of the curve is k. Or if we plot the other part, that is 1 by Ca naught into Xa by 1 minus Xa is equal to Kt. So, in terms of the conversion, if we plot, this would give T, and this part is Xa by 1 minus Xa. So, we will obtain a curve which is passing through the origin with a slope So, the slope of the curve would be Ca naught into k. So, when we have a second order reactions and the reactants are introduced in their stoichiometric amount, we have to treat differently. Now, another question for this type of analysis is that the kinetics of the reactions or the reaction kinetics as well as the stoichiometry, how that influence the analysis of the integral methods. So, integrated expression depends on both the stoichiometry as well as the kinetics. Let us take an example. A reacts with twice B and producing products. So, this reaction, if we assume this is second order, that is it is first order with respect to A and first order with respect to B and overall second order reaction, then we can write the rate of reaction minus RA would be equal to minus dCA dt, which is equal to k into Ca Cv, and which we can write k into Ca naught square into 1 minus x a into m minus twice x a. Here m is the ratio of C b naught by C a naught. Now, if we integrate this rate expression, we would obtain ln C b C a naught by C b naught C a, which we have done before. Similar way, in this case also we can get ln m minus twice x a divided by m into 1 minus x a, which is equal to C a naught m minus 2 into k t, and this equation would be valid when m not equal to 2. So, if it is m equal to 2, this is not valid. So, when we incorporate stoichiometric amount of the reactants, in that case the integrated form for stoichiometric amount of the reactants the integrated form would be 1 by C a minus 1 by C a naught, which is equal to 1 by C a naught into x a by 1 minus x a, which is equal to twice k t. So, this is valid when m is equal to 2. So, both from here we can see that both stoichiometry and the reaction kinetics, that is, it is for non-elementary reactions, the reactions of A and twice B producing products, which is considered as non-elementary reactions, because we have considered as second order reaction. Now, if we consider irreversible third order reaction, let us take an example. Say the reaction is A plus B plus D producing products. So, the rate equations we can write for the third order reactions is minus R A would be equal to minus d C A dt, which is equal to K into C A C B C D. Now, in terms of conversion we can write C A naught dx A dt would be equal to K C A naught square K C A naught cube into 1 minus x A into C B naught by C A naught minus x A into C D naught by C A naught minus x A. Now, if we take this equation, differential equation, and if we separate the variables and break down into partial fractions, then with integration and manipulation we can obtain. So, separation of variables, then break down to partial fractions and integration. This will lead to 1 by Ca naught minus Cb naught into Ca naught minus Cd naught ln Ca naught by Ca plus 1 by Cb naught minus Cd naught into Cb naught minus Ca naught into ln Cb naught by Cb plus 1 by Cd naught minus Ca naught into Cd naught minus Cb naught ln Cd naught by Cd, which is equal to Kt. So, this is the integral form of third order reaction as shown above. Now, if we consider any one components in large excess, the same equations will reduce to the second order reaction. So, which we can compare with the derivations we have done, integral form of the red equations which we have derived earlier for the second order reaction. Now, another example of third order reaction is A plus twice B to R with rate of reactions minus Ra is equal to minus dCA dt, which is equal to K Ca Cb square. Now, same thing we can write in terms of the conversion, which is dxa by dt would be equal to K Ca naught square into 1 minus Xa into m minus twice Xa square. Now, if we consider, so here m is equal to Cb naught by Ca naught. Now, if we integrate this relation, we will obtain twice Ca naught minus Cb naught into Cb naught minus Cb divided by Cb naught into Cb plus ln Ca naught into Cb naught divided by Ca into Cb naught, which would be equal to 2 into Ca naught minus Cb naught into square into Kt. So, this equation is valid when m is not equal to 2. Now, for m is equal to 2, if we integrate from here for the third order reactions, then in that case we will obtain 1 by C A square minus 1 by C A naught square would be equal to 8 kT. Now, similarly, if we consider the another reactions of third order, which is A plus B forming R. So, this is non-elementary reactions and of third order, where 1 mole of A is reacting 1 mole of B producing R. This reaction is considered as third order reaction. So, in that case the rate of reaction, if we write minus R A is equal to minus d C A dt, which is equal to K into C A C V square. Now, if we integrate this equation like earlier, we would obtain C A naught minus C B naught into C B naught minus C B divided by C B naught C B plus ln C A naught into C B naught C A naught into C B divided by C B naught into C A, which is equal to C A naught minus C B naught square into K T. So, this equation is valid when m is not equal to 1. Now, for m is equal to 1, we can get for third order reactions 1 by C A square minus 1 by C A naught square would be equal to twice K T. So, this is valid for m is equal to 1. So, these are the two integral form of the rate equations for third order reactions with the different stoichiometric ratio, which is not equal to 1 and one is the stoichiometric ratio is 1. So, overall we can see that the stoichiometry and the kinetics of the reactions are both important to represent the integral form of the rate equations and analyzing the data from the batch reactor analysis. So, thank you very much for attending this lecture, and we will continue our discussion on the batch reactor data in the next class as well.